Hey folks, welcome to this episode on limiting reagents. Now before we get into limiting reagent, let's talk about chemical reactions. When two or more reactants react with one another, they do so in a very specific ratio, and that ratio comes from the coefficients of the balanced equation. Let's say we had reactant A reacting with reactant B, and the coefficients of them, A was 1 and B was 2. So in that case, when we have these reactants, we have A and B, and the coefficients are 1 and 2. That means for every 1 of A, we're going to need 2 of B. And now we're usually talking about moles in this case. So if this ratio is observed, and we provide enough reactants for this ratio to be observed, what we're going to see is that both of the reactants are going to be consumed completely, and there's nothing going to be left over in terms of reactants. However, let's say, for example, we have 1 mole of A, and we add 3 moles of B. Well, the ratio is only a 1 to 2 ratio, which means we don't need 3. What's going to be left over is we're going to have 1 mole left over. So what we say is that this reactant is now in excess. Okay? We had more than we needed, and now we have some left over. So in industry, we try to make sure that all of our reactants are used up completely, because otherwise we have waste and that eats away from our bottom dollar. So what we're really trying to relate is how can we be efficient with our reactants, and if we're not, how much is left over and how much will that limit the amount of product that's made. So let's look at relating this to making meals. Let's say you're in a camp counselor and you need to make packaged meals for the children at camp. So one of these packaged meals consists of a sandwich, okay, a set of cookies, so 2 cookies, and an orange. So what's the ratio between these items in this meal? Well, if we look, we only have 1 sandwich to 2 cookies to 1 orange. So it's a 1 to 2 to 1 ratio. So we could kind of say if we're looking at these as individual things, I need 1 sandwich for every 2 cookies, for every 1 orange to make a packaged meal. So here's our ratio reflected in this little diagram. So we kind of are treating these as our reactants and this as our product. And this is our ratio of our reactants in a sense. And this is our product here. So let's say, for example, you place an order, you told your colleague to place the order, and that person messed up the numbers. They ordered a little bit too much or maybe too little, who knows. But let's say this is what the order came in with. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 sandwiches. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sets of cookies. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 oranges. So 13 sandwiches, 11 sets of cookies, and 13 oranges. So how many packaged meals can you make from this? So if you said 11 packaged meals, you are correct. The problem with this is, as you can see circled here, that we have these 2 sandwiches and 2 oranges that are unreacted. They're left over. Okay? There are no sets of cookies that go along with these. So when we see here, we've been able to create 11 sets of meals, and we have these leftover items. The more important thing, however, to get from this is that what dictated how many packaged meals could be created? Well, we had 13 sandwiches, 13 oranges, and 11 sets of cookies. And what we created was 11 packaged meals. So the reactant that was limiting how many packaged meals could be created were these cookies. Because if we had 1 more cookie, we could create 12 packaged meals. If we had 2 more sets of cookies, we could create all 13 packaged meals and we wouldn't have anything left over. So the cookies are the things that are really limiting how many of these products or the packaged meals that can be created. So in this ratio of 1 to 2 to 1, we needed to follow that to create 1 packaged meal. However, we were limited by the amount of cookies that we had, and our limiting food item were these cookies. Now, some characteristics of it was that it was completely used up. We didn't have any left over, and they also determined the amount of packaged meals that could be created. If we had more of these cookies, if we had 2 more sets, we'd be able to use all of our initial starting ingredients. but we only had 11, so we could only make 11 packaged. This is called our limiting reagent. Okay? And our limiting reagents are always completely used up, and they determine the amount of product or the amount of packaged meals that can be made. Now, because we only had 11 sets of cookies, we had some of these left over, and so these are our excess reagents. Okay, these are our excess reagents, and they are things that are left over at the end. Because we only had 11 sets, we could only make 11 packaged meals, and so these other two were not reacted. So let's relate it to a chemical reaction, and this reaction is called the Haber process. This was invented by Fritz Haber, and it's used to make things like fertilizer and also used in explosive production. So it really was an industrial way of fixing atmospheric nitrogen. So that's a very, very slow process in the environment. This allowed us to fix atmospheric nitrogen into ammonia. So what we did is that we combined hydrogen gas with nitrogen gas to create ammonia. Now obviously this is not a balanced reaction. Let's go next and let's see how we can balance it. So we have two containers here. We have some with hydrogen and some with nitrogen, or both of them with hydrogen and nitrogen, but in different proportions. You can see right away that we have the same amount of nitrogen molecules, 5 and 5, but you can see that also the amount of hydrogen molecules, there's more of them here than there are here. So which one is going to go in completion? What we mean by that is which one will allow the reactants to be fully utilized. So again, when we look at this reaction, we first have to balance it in order to see what the ratio is. So in this case, I have 2 nitrogens. I'm going to put a 2 here. That makes 6 hydrogens, so I'm going to put a 3 there. And that also I have 1. So in this case, my ratio between reactants is 3 to 1. For every nitrogen molecule, I need 3 molecules of hydrogen. And when I have that ratio, I'm going to make 2 molecules of ammonia. So the container that will allow us to utilize all of our reactants will have this 3 to 1 ratio between hydrogen and nitrogen. So let's go ahead and look at our containers and see what our ratios are right now. So in terms of my nitrogen, I have 1, 2, 3, 4, 5. So container number 1, I have 5. And for my hydrogens, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, so I have 15 to 5. So if I distill that down, if I simplify it, it's 3 to 1. Okay, well that seems to be okay. Let's look at the other one. So in this one, I have 5 molecules of nitrogen. So 5 here. And I have, for hydrogen, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. There's not really much I can do with that. There's no kind of a common factor. So my ratio is 9 to 5. Now, let's say, for example, is there something that I can do to kind of factor this out? Well, what's a common number between 9 and 5? Nothing. How about 9 and 4? Nothing. How about 9 and 3? Oh yeah, there we go, 9 and 3. So if I did 9 and 3, that would be distilled to 3 to 1 plus 2 extra nitrogen molecules. So we could have a ratio here, but it seems like we're going to have something left over. Let's see if that's actually the case. So for container 1, again, our ratio is 3 to 1 for nitrogen, and that will create 2 molecules of ammonia. And what we can see here is encircled is that we have a 3 to 1, 3 to 1, 3 to 1, 3 to 1, 3 to 1. So we had our 15 to 5, and that reacted completely. And notice how we're forming complete ammonia molecules after the reactant. So all the reactants have been completely consumed. There's nothing left over. So technically what we're seeing is that both of them are kind of limiting reagents. They're both controlling the amount of reaction. We have a perfect proportion of nitrogens and hydrogens. When we look at container 2, however, we can see that we have 1 nitrogen and we have our 3, 1, 3, 1, 3. But like we said, we had to remove 2 nitrogen molecules from that to get a good ratio. And as you can see is that we do produce our ammonia molecules, but we'll have some N2 left over at the end of it. So in this case, we can see that the hydrogen was completely used up. There was no hydrogen left over. And the amount of hydrogen actually dictated how many molecules of ammonia had. If we had more molecules of hydrogen, we could possibly use these other two molecules of of nitrogen to create ammonia. But because we didn't have any more hydrogen, the hydrogen is limiting how many products can be made. It's being completely used up, and it's controlling how much ammonia is being made. Therefore, we call it our limiting reagent. Because N2 is not fully reacted, there's still some left over unreacted. That is our excess reagent. So in this case, we did have a stoichiometric ratio met, but we also had more than what we actually needed. And so in this case, the ratios were not fully or completely met, so we had some left over as an excess. All right, so let's apply this into an actual reaction here. Here we have methane reacting with water to form hydrogen and carbon monoxide. So the first thing that we want to do is we want to start off with a balanced equation. So we have CH4, and that's a gas, reacting with H2O in liquid format to produce hydrogen gas, H2G, plus CO, and again that is a gas. So to balance this, our carbons are balanced, 1 and 1, our oxygens are balanced. Here we have 2 hydrogens, and collectively here we have 6. So we could put a coefficient of 3 to balance. Now to help with our ratios, we're going to put a coefficient of 1, 1, and 1, just to visualize these ratios a little bit better. So what is the stoichiometric ratio between the two reactants? Our reactants again being CH4 and H2O. It is a 1 to 1 ratio, and that just comes from the balanced coefficients. So when it comes to a question like this, if we have 10 moles of methane reacting with 17 moles of water, which one is the limiting reagent? Well, I'm just going to do a little hypothetical situation here. CH4 and H2O. So if CH4 was our limiting reagent, and I had 10 moles, how many moles of water would be needed to react with? So if it's a 1 to 1 ratio between CH4 and H2O, and I had 10 moles of CH4, I would need 10 moles of water. Do I have that? I do indeed. I actually have 17 moles of water, so I have more than I need. If I was to hypothetically do it the other way and said that H2O was my limiting reagent, that means that all 17 moles of H2O would need to be used up. That means, again, based on this 1 to 1 ratio, that I would need 17 moles of CH4. Now, do I actually have that? I don't. I only have 10 moles of CH4. So this reaction is impossible. The only one that would work is if CH4 is our limiting reagent, and I would need to react 10 moles of water. So that means that our limiting reagent, or limiting reactant, is CH4. The excess reagent is going to be H2O. And how many moles of it is left over? Well, we have to see how much of the excess reagent we had and how much we used up. So initially, we actually had 17 mole of water. Now, because CH4 was all used up, it used 10 moles. It also, based on this ratio, 1 to 1, needed 10 moles of water. So 10 moles of water was used up in this equation. So if I subtract what I used from what I initially had, I would get what is left over. And 7 mole of water is left over. Now, when it comes to seeing how much product will be made, the same ratio applies. In this case, we have to look at our limiting reagent. Our limiting reagent, and the value of the limiting reagent, this 10 mole of methane, is the golden number. Okay? Everything is calculated off of this number. How much product is made, how much of the other reactant is used, everything revolves around this number because it is the limiting reagent. It's directing the entire reaction. So what we have to look at is how many moles of CO compared to moles of CH4. And based on our balanced equation, again, it's a 1 to 1 ratio. So if I completely use 10 mole of CH4, that means I'm going to produce 10 mole of CO. Now this could also be done in a dimensional analysis. I had 10 mole of CH4. And again, I put my unit that I want to get out on the bottom, mole of CH4, and the unit that I want to be left with on top, mole of CO. I look to my balanced equation, and it's a 1 to 1 ratio, so I can fill those in, 1 to 1. And that means my units will cross out here, and I'll get 10 mole of CO. The same thing can be done with water. Again, my limiting reagent is the value that I need because it's directing the entire reaction, so 10 mole of CH4 And again, I want to put my mole of CH4 on the bottom because I want to get rid of it, and my mole of H2O on the top. Oh, excuse me, not H2O, H2. So again, I go back to here and I look at what the relationship is. I have 1 mole of CH4 for every 3 moles of H2 produced. So it's a 3 to 1 ratio. My units will cancel out, and I'll get 30 mole of H2 produced. All right, folks, thanks very much for watching. See you next time.